Hi again, everyone. So we'll continue from where we left in the previous class. In the previous class, we did these two levels. We saw how to represent negative numbers in binary, and we did this binary eraser. And we also did an input selector. So I would consider the previous class as a bit easy. So for today, and on this input selector, we are using this bit to determine between these are bytes. If you see this huge thing, this is a byte, and the small one is a bit. A bit is just one electric signal. A byte is 8 channels of the same to represent some value or something in binary. So we saw that we can use this and select this being off. It selects this, and it being off, being on. Okay, no, it being off, it selects the first byte, since we're using negation and not get to enable this channel. And it being on, it in turns uses this path, and this is what is called a multiplexer. And yeah, we're going to see how this will be used to develop, I guess, even a bus in a computer. A bus is essentially just one channel that a lot of let me say peripherals or inputs like this byte and this byte are going to use the same channel, but on different times. So yeah, today's class will be signed negators. And that's true, we have a bus, but let's start with this signed negator and see what it's about. The level says taking the input as signed, where the 8th bit is negative 128, making the component that takes a number and negates it. For example, 4 signed, for example, 4 negated will become negative 4. Negative 9 negated will become 9. So yeah. And we saw that here, this eraser, by this being on, that means this whole number is negative instead. That is for signed integers, not integers. For signed numbers. So I think we'll see how this concept interprets to having the programming types that we have, the variable types like integers, and we have signed integers, and why having them assigned, they reduce the amount of values that we can represent using a set of bits. So for like this, if we have 8 bits and we are declaring as this not being signed, that means that we can represent up to 255 values using just these 8 bits. But when we declare this as assigned, that means we have to cut the numbers we can represent by half. So we can't represent numbers above 128. That's why we have this, because half of the numbers represent positive numbers and half of the other numbers represent the negative numbers, and this is what determines that. But we are going to see that later on when we get into programming of these computers. So for this stage, let's see what this is about. I didn't even get the instruction. Taking the input assigned, where the 8-bit is negative 128. Make a component that takes a number and negates it. Okay, so and we're given how the procedure of negating, for example, 4 will be negative 4. Okay, we're not given the procedure but the instruction. So essentially, these are bytes representing a number like, let's say, I don't know, 56. And essentially we should get negative 56 here, right? So to negate it, according to what we can see, is that we only take the most significant, the last bit on top and invert it. So from the 8-bit we took a byte splitter, and then we should also take a byte maker to send everything back as it was. That's 8, 24, 56, which is okay. That. But now we need to invert this last bit, the most significant one. And I think, I'm not sure if this is how we do, but let's see. Okay. So to represent 56, we should get a negative 56, ideally. And how do we do that? Again, the log level says taking the input assigned, whereby the 8th bit, which is 1, 2, 3, 4, 5, 6, 7, 8, is the 8th bit, makes as we saw, it was like, I think, inverting. I'm not sure, but this should turn it to negative, but negative 72. But that should not be the case. So how about because this is if we want this to be okay, let's try making a negative 56 from here. This is an always on component. That means by turning this on, I have negative 128. Turning this, for some reason this level crashed, so It says so. Okay, I think I need to create another schema. Let me just say test. Okay, and we'll start over again. The instruction is to take the input and negate it. Make a component that takes a number and negates it. So and the way we negate it is essentially by just adding a 1 in the most significant bit, right? Like if this was 56, then having this as on, we had, hope it's not gonna crash again. And we can toggle the format to see the negative numbers. So this is negative 128. We're going to 32, 80, 72, 68, 66, and that does not even get me to Okay, we'll just scrap this idea and how about we flip the whole bit, because to represent sign numbers, what I know is that we're supposed to take the number and that's, yeah, we negate it, and we can see we get negative 57, but we're supposed to get negative 56. So it's essentially the two complement says that we note the byte and then we add a 1. So maybe try adding a 1 to the output. So we have negative 57 flowing this through this adder, but to add a 1 we can use the same on that we are using. It's just a 1. This is a bit, is a single bit, not a 8 bits. And now we have our negative 56, because even on the eraser, binary eraser that we had for the negative kind of numbers, we saw that the values representing them in binary, they were short by 1, right? And only when we discovered that it was off by 1 bit is when we were able to get the number we want. So the formula is this simple: is you take your byte, which is 8 bits, you negate it, which is inverting it, we get a negative 57, but then we have to add a 1. So we take an adder. This is an adder, 8-bit adder, but now with just one input. It doesn't matter where it's plugged, here or here. Then we add a 1, right? So the result is negative 56, which is what we have. And the level says that if we use a 4, we get a negative 4. Use a negative 9, we get a 9. So let's use a 4. We get a negative 4. Let's use a negative 9. Let me see if we can get a negative 9. We should get a 9. Negative 9, it's made to be an 8, then added 1 becomes a 9, which is okay, and it applies to everything. That's how we have signed negators. And I believe that's it for the level. And you can see it should pass all these conditions. And now we have a new component. This is know that this is different from the not. We have a not which negates the bits, but then we have a negative, which it's a negate plus 1, which means it's a negative number, representation of a negative number. Whatever passes through here, the input, and goes to the output, it's converted to the opposite sign, which is the negative one, right? And that level has been a bit but let's see the next level, which is the bus. As we saw in the previous one, the fact that we can select between whatever bytes. If we had another one, we could probably have another, we could add another 2 bytes, and then we could have another bit instruction to determine what kind of what input to select on this. Use the multiplexer, the MUX. And so we notice that we can just use this one channel, this one output, to select and use this instruction, this bit, to select more. So adding another instruction adds 2 of these, and we can add another one, adds another 2, and now we have 6 to that, and they can all use this one communication channel, which in a previous class we see an introduction to something called the bus. So this level has 2 byte inputs and 2 byte outputs. Okay, your goal is to copy from one of the inputs. You can either copy from one of these to copy from one of the inputs to one of the outputs. Yeah, and I guess these are the instructions to determine the first bit, which is this. The first bit input determines which input you should copy, which input you should copy from. Okay, so if maybe this is on, says maybe this. If off, maybe says this. And the other, the second bit, which is this input, determines which output you should copy to. So this is going to determine where the thing goes to, right? This byte. And now things are getting a bit interesting. So we have these bits acting as instructions, right? So okay, let me see. Okay, so as we can see here, this, which is from, right now says 0 in 0. That means that the one that should be selected, and we are given a limit of the components we should use. So we have 4 switches. We can have our first switch, this going to here. It's just like the previous one, and then another one, maybe extend a bit so we have a bit of space. And now we are told that right now this is 0 in 0, this is in 0. You can see the label in 0, and this is in 1, in 1 and in 0. So we are told that, okay, let me do, okay, we're told that if this is off, in 0 should be selected. So off, and the way we select this is we also have negation. Take this NOT gate, and we get a signal from there which is on. That means that it goes somewhere, right? And this somewhere can be can be, let me just leave it that way. So if we had a number over here, 56 in binary, something like this. Okay, this is negative. Let me just input 56. I don't know, I like it. So that means that if this is off, we select the 56 to go to this channel. Let's call it maybe the bus now. And if it's on, that means everything is inverted and the signal now comes in to the other one. So here, let's say we had 12, or even better, let's make use of what we have learned and have a negative 12. So we have, by just switching this on and off, we are selecting what to use. Right now 56 and 12, and we can even do better and combine them together and have just something that looks like one output, like this, so that we can clearly see. And since these they're not really active at the same time, because we have this enable pin, which is, you can see it's the enable pin. That means that it's like, if it's off, that means it's like the components, even that Y is not even there. And if on, then it's active, right? So by just switching this on and off, we are able to change the value here from 56, negative 12, 56, negative 12, 56, negative 12. That means now we are able to choose between the inputs, the two inputs. Now we have a bit of control, and we are told that this does the same but for the outputs, right? So if right now it goes to output 0, which I believe is the first one, this one, right? Let me try reset again. This was 56 and negative 12. And now switching that, we are okay. But now we also need to use this signal Now we have also 2 of these other switches. Let's try reducing this something smaller, so we can select there. Maybe just use it from here and see how it goes. Oh, I think it should be from here, because we have these and maybe these. Let's assume this goes to here, connect this as well. And now we want to use this. So for now, this one says that we're selecting 0. So taking this when off up to here, and then using this negation to power this, that means we are selecting this. So 56 goes to the first one. And otherwise, if off, does the opposite, which now picks this signal to here. And now we have 56 going to the second one, 56 going to the top one, bottom one. And if I want 12 to go to the bottom one, I just select the bottom one and select 12. And that's it. We're able to move data from wherever we want. And we can test that. It says copy the value from input 1, which is this. In computing, mostly we have to start with 0. We start with 0 and 1. So if you see we're saying input 1, we don't mean this, we mean the second one. So we are copying this value 20 from input 1 to input 0. 20 from here, closing through this channel, and again to the top, which is input 0. And now we are able to control whatever we want, and we can test everything else. And that's our bus level. And onward. And I think that's about it for our class. We'll continue from saving gracefully in the next class. So bye.